Okay, so let's start. Okay, so today I wanted to talk about associated sheaf functor. Okay, so let's fix the setup. Let's see be a small category J and Grothendieck topology on C. Finally, we have an inclusion from sheaves to re-sheaves on this category. So full subcategory of G sheaves on C. I formulate the key theorem of this of my today's talk. So inclusion functor has a left adjoint A from pre-sheaves to sheaves. And this functor additionally commutes with finite limits. So yeah, this is the key theorem. Basically, what we can say is that the subcategory of sheaves inside of the category of pre-sheaves is reflective in the sense that we have a reflection of each sheaf to this category given by this functor A. This functor is sometimes referred to as sheafification of a pre-sheaf, and I will describe a construction which yields precisely such a functor. Okay, so small subsection plus construction. Please do not think that it has something to do with plus construction from K theory. It's just a name. I guess even this name is specific to the book I'm reading. I'm not sure that it is used outside of this book on sheaves. I never saw it before. So I guess this is just their notation for what I'm about to describe. Okay, so the first thing we do is that we define definition separated pre-sheaves. Separated if for any matching family there is no more than one amalgamation. So if we compare this notion with the notion of a sheaf always has a unique amalgamation, and here we may not have an amalgamation, but if we have one, it is unique. Okay, so now the construction of this A functor proceeds in 2 steps. The first step is that we construct, so what we do, we have a pre-sheaf, we construct P plus, also a pre-sheaf, but now it is a separated pre-sheaf. And then we show that if P is separated, I'm just sketching a scheme of proof of this theorem. If P is separated, then P plus is a sheaf. Then A of P is defined as P plus plus. Okay. So let's.
Sorry, what is a P plus?
P plus, I did not define it yet. It's some construction which yields a separated pre-sheaf from a pre-sheaf. I will define it in a moment.
Okay.
Okay. Thank you for the question. I just sketch how we will prove this theorem. So the idea was to pass from pre-sheaves to separated pre-sheaves, and then from separated pre-sheaves to sheaves. But now I will give a motivation for definition of P plus, and then I will define P plus. So to understand the definition of P plus, we first observe that if P is a sheaf, then for any cover R of an object C in C curly and for any matching family of elements of P there should be a unique X in PC, which is an amalgamation of this family. Moreover, if okay, so we have a unique amalgamation X here. Moreover, if P is a sheaf, and S is a sieve in growth-index topology J, which refines R, meaning that we have S in R. Then subfamily XF, F, and S, which is precisely subfamily in this guy, should represent the same element. So the idea is that if you have a cover and then you have a finer cover inside of it, if you have a finer cover inside of it and you have a family of elements on the large, on the larger sieve, then when we restrict ourselves to the smaller sieve, we once again get the same element because, basically we just have two covers with equivalent sections over them. So that's one simple observation, and this observation allows us to define P plus finally. So if P is a pre-sheaf, if P is a pre-sheaf, then we can define P plus as a colimit of the following form. So what is match RP? Well, match RP is a family of matching families for P and sieve R. So better still, collection of matching families for cover R and pre-sheaf P. And it's ordered by reverse inclusion because, as I pointed out, if we have a finer sieve, then we can just restrict the matching family to its subfamily, and thus we get a colimit. So yeah, this is the idea. We can reformulate the definition of individual elements in P plus. So class of equivalences of matching families This the last condition is just a definition of matching family. So for all k from E to D. So two families are equivalent. Two families X and Y are equivalent if there is a common refinement. T in RS, where T belongs to J of C, such that over this finer covering there is an equality of elements. So P plus defined in such a manner has a structure of a pre-sheaf the restriction morphism is given by P plus of C goes to P plus of C prime for H from C prime to C. We have a formula of the following form. So we have an element which is represented by this family, this matching family. Then we just map them to a family which is defined like this. So this is a well-defined map on equivalence classes of such matching families. Okay, so what we did, we actually defined a functor or an endomorphism of the category of pre-sheaves. And we have a natural transformation from the identity functor to this plus functor. So if we have an element of valued on a section over C over pre-sheaf P, then we can map it to the following family, where TC is the maximal sheaf, is the maximal sheaf on C. Okay, so let's consider an example of this construction. It may seem a little too abstract, so I will give an example. Consider topological space X with topology of x given by open covers. Consider a pre-sheaf B on X consisting of bounded functions on X. That is B of U consists of bounded maps from U to R for any open subset U. Clearly, this pre-sheaf may not be a sheaf because we can consider a cover where over each individual element of a cover the function is bounded, but it is not bounded over the whole topological space. For example, consider an open array of positive real numbers and consider a function 1 divided by x over this array, and clearly we can construct a cover where over each individual element of a cover the function is bounded, but it is clearly not bounded over the whole space of positive real numbers. So we want to consider a plus construction on this pre-sheaf. Consider a sheaf C of continuous R-valued functions on X. This, on the other hand, clearly is a sheaf. We already explained last time that we have that for any topological space, the representable pre-sheaf is a sheaf in the topology of open covers. So yeah, this is a sheaf. And we can construct a natural map from B plus of U to C of U given by, well, if we have a matching family of bounded functions, then they glue together into a continuous function. So we have a natural map from B plus of U to C of U. And conversely, for any C of U, for any element, so for any F and C of U, there is matching family of bounded R-valued functions representing F. How do we construct such a family? Well, we consider Fn from Un to R, where Un is given by condition that f of x, modulus of f of x is strictly less than n, and Fn is obtained as f restricted to Un. that is, we've proven thus we've proven that plus construction on bounded functions yields all continuous functions. However, it may seem that it is sufficient to do only one plus construction on a pre-sheaf to obtain a sheaf, but actually this is not true. And in fact, I will provide an example where one iteration of plus construction is insufficient to obtain a sheaf. So so constant pre-sheaf of a set S. So P of U is equal to S for any U open on X. And all restriction morphisms are identities. So P of U is equal to identity S. Okay, so let's take a first iteration of the plus construction. Then P plus of U consists of S for U not equal to empty set, and consists of singleton set for empty set. Why is this? Well, because when we take a matching family on an open subset, then clearly all elements should be, since all morphisms are identities, then all elements of all matching elements are the same element, and so we obtain S. And for empty set, there is only one matching family, the empty one, and thus there is only one element in P plus of the empty set. So let's observe why this is not a sheaf. Thus P plus is not a sheaf. Since for two disjoint open subsets U1 and U2, X U1 and X U2 restrict to the same element in U1, U2 equal to the empty set, because the value on the empty set is just a singleton set. However, we can't glue them together into an element or on U1, U2, because as we seen earlier, the value on U1, U2, U1 united with U2 should be S, and thus they should be the same element in S if they're a matching family, if we have gluing. However, if XU1 is different from XU2 as an element of S, then we can't glue them together. So one iteration of plus construction is insufficient to obtain a sheaf. However, now we will see that if we iterate the plus construction 2 times, then we obtain a sheaf. So equivalence class of matching families Si in PUI such that psi is equal to Sj for UI intercepted with Uj not being an empty set. Thus, such elements glue together psi glues together into S from U to S with a property that each point of U has an open neighborhood UI such that S is constant on it. So S from U to S is a locally constant function. And P++ of U is a set of locally constant functions on locally constant functions on U. So what happened here is that is that we added all sections that were not present in the initial pre-sheaf, and we obtained a new sheaf which has all these sections. So it's like a usual idea of sheafification that you add all sections which should be present, but they're not, and you obtain a sheaf. However, here we developed this formalism of matching families, which allows us to handle this agent of sections more formally. Okay, so yeah, so are there any questions so far? Okay, if no, then I will formulate several lemmas. You have to bear with me because they're quite technical, but these lemmas will allow us to prove theorem, well, this key theorem about existence of this functor A and its property of commuting with finite limits. Okay. So lemma. First, sheaf is separated if and only if eta from P to P plus is an injection over all open subsets. Second, a pre-sheaf is a sheaf if and only if eta from P to P plus is a bijection. Okay, so let's prove this lemma. It's not very hard to prove. Let x and y be elements of P of C for some object C and C naught. Then for C0, then eta of x is equal to eta of y. So we're proving first assertion. Then eta of x is equal to eta of y if and only if xf is equal to yf for any f in S for some sheaf S. Thus, x is equal to y if and only if P is separated. So x and y are amalgamations of respective families, and the amalgamation is unique precisely when the pre-sheaf is separated. Second assertion is proved similarly. Okay. So the second lemma if f is a sheaf, P a pre-sheaf, then for any phi from E to F, there is a unique factorization through eta like this. So we have this diagram. Like this. Okay. So let's prove this lemma. An element p plus of c is represented by a matching family or some are covering C. Then for any h from D to C in R, definition of eta shows that at the D of xh is equal to xh dot k, where k belongs to a maximal C from D. That was just the definition. On the other hand, except for f and r dot h is equal to the following. But h star r is equal to T of D because h belongs to R, and thus we have yeah, so this is clear. This is because h belongs to R, and thus we obtain the maximal C. And thus xf, f, and R is a matching, and we obtain an equality thus we obtain this equality. So if phi tilde exists, phi tilde of this thing should be a uniquely defined element since f is a sheaf. And since it is an amalgamation, we should have the following property that YH is equal to phi xf f and r h equal to phi tilde of d of xh equal to phi of xh for all h and r. Such y in f of c exists since f is a sheaf such y exists because f is a sheaf and this thing here is a matching family. So let's once again go through this proof. What we did here is that we said that an element of D plus of C is represented by a matching family for some covering of C. Then for any element, for any map in this covering, definition of the natural transformation eta shows that eta D of this xh is xh dot k for h in T of D, for k in T of D. On the other hand, we've shown that we see that since h is in R, h star of R is equal to T of D, and thus this restriction of this matching family along H is the same as well, wait a moment. So yeah, we've shown that by definition of this operation of restriction, we see that this is a matching family, and we obtain an equality that this transformation of xh is the same as the family which represents our element x multiplied by h for any h in R. Then we observed that if this map phi tilde, which was a map from P plus to F, map from P plus to F, exists, then we should have an amalgamation of a matching family into a unique element in F of C, such that the restriction along each H is the same as restriction of this element along H, and in turn this should be the same as the restriction This should be the same as at the d of xh, because we observed this earlier. And thus, this in turn is the same as phi of xh for all h in R. And finally, we observe that such an amalgamation exists because a family phi of xh is a matching one and f is a sheaf. Okay, so we observed uniqueness and existence of phi tilde. Okay. Now let's move on to the next lemma. So this proof was a bit technical, so you may just remember the formulation of this lemma, that this P plus is a universal construction which gives us the map to a sheaf from a map from a pre-sheaf to a sheaf. Okay, another technical lemma. For any pre-sheaf P, a pre-sheaf P plus is separated. Let's prove this. Let us show that P plus is separated. That X and Y in P plus of simply two elements. Such that their restrictions coincide for some covering sheaf Q. We want to show that X is equal to Y. Let's represent these two elements via matching families. So R and S are some covering sheaves for J to, for the polyg J. So it means that we have refinement T, a common refinement, TH, sorry, a common refinement of the pullback sheaves HR and HS on D, such that x ht is equal to y ht for t in t of h. However, the transitivity axiom for covers imply that t equal to ht for h and q and t and th is a cover of C, and the inclusion relation is preserved by pullbacks. So x is equal to y in p plus of C. So we've proven that a pre-sheaf p plus is always separated. Okay, so the final lemma, the hardest one. If P is a separated pre-sheaf, then P plus is a sheaf. Okay, so let's prove this lemma. To show that P plus is a sheaf, we should glue an arbitrary matching family X covering R. So this matching family looks like this. And xf belongs to P of D, where f is from D to C. Each xf is in turn defined as an equivalence class where G is from E to D. And SF is some covering of XF is a matching family, means that for any H from D prime to D, we have XFH equal to xfh. As elements of P plus P prime. Using the definition of this guy here, we have an equivalence class x f h g prime. G prime belongs to h star of SF. And this is equivalent to xfh g sfh for all g contained in sfh. This equivalence means that there is a cover tfh inside of h star of sf intersected with h star intersected with sfh for d prime, such that xfh xhg prime is equal to xfh g2 primes for g2 primes in tfh. Let's denote this equation by star. We will need it later. Let Q be defined like this: F in R, G in SF. R and SF are covers of C, hence Q is a covers, hence Q is a cover of C. Let us define Y bold in P plus of C by the following equation. We want to show that this Y bold is in fact an amalgamation of the family X. So to do this, we have to show that this definition does not depend on a specific factorization Fg. So assume that Fg is equal to F prime G prime for some F prime in R and G in SF, G prime in SF prime. Then if K belongs to TFG intersected with T prime G prime, then XFGH is equal to XFGH since XF is matching. This in turn is equal to XFG H sorry, xfg k. Write it like this. So this is by star. What we had here, well, we had this equality, and we observe that this is precisely the equality we get here. So by assumption, we have an equality like this. Now, by star, we have equality like this. So we may interchange G and comma by star. Finally, since xf prime is a matching family, we have an equality that we wanted. So this shows that, in fact, Y is well defined. Thus, since xf is a matching family, it follows that Y equal to YH HQ is matching. Then it is an element of P plus C. We claim that Y bolt is an amalgamation of xf. For this, we need to show that for any f from D to C in R, Y bolt dot F equal to Y FH, H in F star Q, and XF are equivalent. This is true since SF is a subsheaf of F star Q. By definition of Q, for any G and SF, Y fg is equal to x fg by definition of y. And this implies that the amalgamation exists and it is unique. Okay, so we're done with this laborious lemma, but the gist of it is that we've proven that a separated pre-sheaf yields a sheaf under this plus functor. Finally, we can deduce the theorem. So as promised, we define A of P as P plus plus. It is a sheaf since P plus is separated. And it satisfies the universal property of left adjoint to the inclusion because we've proven the lemma about the universal property of morphisms to sheaves. So home and sheaves of A of P to F is equal to a home in pre-sheaves of P to F. Thus, we've proven that it is indeed a left adjoint. And so we've constructed a left adjoint. Now I will provide a simple corollary, and we will finish the proof of theorem by showing that it commutes with finite limits. So composition A iota from sheaves to sheaves is isomorphic to identity functor. This follows from the fact that P plus of P is a sheaf precisely when that P is isomorphic to P plus precisely when there's a sheaf. So it is isomorphic to identity functor. And finally, we want to show that A commutes with finite limits. We showed for the plus functor. So the first observation is that much of RP preserves all limits, it follows from the fact that actually match RP is nothing else than a home set in pre-sheaves from R to P. Since R is a sheaf and it is naturally a subfunctor in the unit of functor, in the unit embedding of an object on which it is a sheaf. So it is a well-defined notion. Finally, we make a simple observation that defined as a filtered colimit of match RP thus commutes with finite limits. It's P to P plus preserves finite limits. Okay, so we've proven the theorem, and that was all that I wanted to say today. Maybe there are some questions, comments, suggestions.
Grisha. So my question is, see if we compose sheafification twice, right, we end up with sheaf, and isn't there any kind of easy description of this twice of composition?
No, I don't know. I don't think that there is in general an easy description of this. Maybe for topological spaces you can say like that you take stocks and you combine them into a sheaf. But I don't think that for general Grothendieck topology there is some easy description of this two times plus construction. No, I don't know. Maybe there is, but I just don't know. I'm sure that for topological spaces you can indeed obtain sheafification in a much simpler fashion. But for general Grothendieck topologies, I don't know such a description. Okay, thank you for the question.
Yes, thank you, Grisha.
Okay.